Today, we're finding a special index in an array. Imagine a point where the sum of all numbers to its left perfectly balances the sum of all numbers to its right. How quickly can you locate such a pivot, or determine if one even exists? The problem asks us to find the middle index in a given array of integers. A middle index is defined as an index where the sum of elements strictly to its left equals the sum of elements strictly to its right. If no such index exists, we should return -1. Important edge cases: an empty left sum or an empty right sum is considered 0. We need to return the leftmost such index if multiple exist. A straightforward approach involves iterating through each possible index. For every index, we'd calculate the sum of elements to its left and the sum of elements to its right. This means nested loops, one outer loop for the potential middle index, and two inner loops for calculating the left and right sums. This repeatedly sums subarrays, performing a lot of redundant calculations. For an array of size n, calculating sums for each index takes roughly n operations, leading to an overall time complexity of O, n squared. Space complexity would be big O of 1, constant time as we only use a few variables. The key insight to optimize this is realizing we don't need to recalculate sums from scratch every time. We can maintain a running sum. First, calculate the total sum of all elements in the entire array. Then, iterate through the array once more. As we move from left to right, we'll keep track of the left sum, the sum of elements encountered so far before the current index. The right sum for the current index can then be derived. It's simply that the total sum minus the left sum and minus the current element itself. If at any point the left sum equals this calculated right sum, we found our middle index and can return it immediately. Otherwise, we update the left sum by adding the current element, preparing for the next iteration. Let's trace this with the example array 2, 3, -1, 8, 4. First, calculate the total sum, which is 16. Now, initialize left sum to 0. At index 0, value 2, right sum is 16 minus 0 minus 2, which is 14. 0 does not equal 14. Update left sum to 2. At index 1, value 3, right sum is 16 minus 2 minus 3, which is 11. 2 does not equal 11. Update left sum to 5. At index 2, value -1, right sum is 16 minus 5 minus -1, which is 12. 5 does not equal 12. Update left sum to 4. At index 3, value 8, right sum is 16 minus 4 minus 8, which is 4. 4 equals 4. We found our middle index at 3. For the array 2, 3, -1, 8, 4, the middle index is 3. At this position, the left sum of 2 plus 3 plus -1 equals 4, which perfectly balances the right sum of 4. You'll spot this prefix sum pattern when a problem asks for sums over contiguous subarrays, especially if you need to repeatedly calculate sums up to a certain point or sums of elements on either side of an index. Anytime you see sum of elements before x or sum of elements after y, think about pre-calculating or maintaining a running sum. This optimized approach has a time complexity of big O of n because we iterate through the array twice. The space complexity is big O of 1, constant time as we only use a few constant variables. This prefix sum technique is incredibly versatile. Try the next problem involving subarray sums, same pattern applies. Make sure to subscribe for more concise DSA explanations.